Let's record this thing. I think it's recording. It says it's recording. Okay. So I'm going to share my screen now. Okay. Now let's get to it. So I'm going to be talking about two things before we go to simulations. We're going to talk about motors and we're going to talk about stability. So let's see. Here's the motor. It's like a typical notation of the motor. You've got some letter at the front, then you've got a number, and you've got another number. So the letter denotes total impulse, and I'm going to explain in a moment what that is. Then the first number is average thrust in newtons, and then the next one is time delay. So I'm going to start with total impulse just to explain you guys what that is. Let me just find the right slide. Just using my slides from last year. Okay, there we go. So what you see in here is a thrust curve. You'll get to see that a lot. Every motor has its thrust curve. And the thrust curve is essentially, it essentially shows what thrust you get at any time instance of the operation of motor. And the area under that curve is total impulse. It essentially tells you how high your rocket's gonna go. So if you have double of the impulse, you can expect that your rocket should go double as high. But also if you change motor, a lot of things changes. So it's not that accurate. So if you want to calculate total impulse, you may do integration, or you could approximate with a rectangle. So if you took average value of thrust and multiply it by burn time, it's going to give you total impulse. So in that case, roughly it would be like 250 times 7 or 8, should be around 2000 Newton seconds. Okay, so I already mentioned this. You can approximate by rectangle. Here's the sample calculation. You may hear in industry about specific impulse quite a lot. So specific impulse, it's a very weird quantity. It's the total impulse divided by mass flow rate and g, acceleration. Let's skip that. Okay, high power motor classification. High power rockets start from letter H. So obviously you've got A, B, C, D, E, and so on. And those are model rockets. We're probably not going to be using those. Michael was using G last time. Actually, he was using the most powerful motor he could in mold rocketry. So he was pretty much ready to do his level 1 certification last time during Midwest Power. So you can see that these numbers double. So each next letter is like double total impulse of the previous one. So you can expect that your level 2 will be about 4 times as powerful than your level 1. Okay. So to give you an example, just to practice, Peter, would you like to calculate the total impulse for the first motor? Would you like to? Because I'm not going to force you if you don't want to. Peter, are you there? No? Okay, what about, sorry man, how to pronounce your name? Satyet? Satyet, do you have any short for it? Are you there?
Peter's here. He's just in the chat, the voice chat.
He's on the chat. Okay. Did he write anything? Cannot see.
Yeah, he said he's gonna try.
Okay. Okay.
And Saita said 250. Question mark.
Let's see. Yeah, approximately 250 is good. So we've got 125 times about 2, that's 250. Okay, the next one. Try once again the next one. Chat. Oh, there it is. Okay. 35. Yep, seems about good. So yeah, you know how to do this. I'm glad. Okay, so that's it. And now let's go to this part. Okay, so you know what is total impulse, you know what is average thrust. Now time delay. Let me see. I should have some diagram on my computer. Not this one, this one. Okay. Can I zoom in? No. All right. So ignore the nozzle for now. Rocket motor consists of 3 parts. The main one is the propellant. And propellant, well, actually, propellant burns, typically it burns radially. Let me just edit it with paint. Okay, I'm gonna zoom in. So actually this entire thing should be hollow. So this entire surface burns all the time. It's not the best color. Maybe let's use yellow. This burns and this burns, and like burns radially. The igniter is somewhere here. And as soon as you ignite this burns, and also this thing burns. The blue thing is the delay charge. And what it is essentially very similar to propellant. It's some mixture that is supposed to burn for some specified time. Let's say 4 seconds. And after 4 seconds, the ejection charge, which is black powder, is gonna explode, and those gases are gonna push out the parachute. So this is the most common way of recovery. You basically use black powder to deploy your parachute. So this number that I just showed you, 4, that means that the blue thing is going to burn for 4 seconds. And you can adjust that. There are tools that allow you to drill from this side, and that's going to shorten the delay time. And that's going to be very important for your simulations. Yeah, so it's important to keep in mind that burn time is not delay time. There are 2 separate times that added together should be apogee time, because ideally you want to deploy your parachute at the apogee. Okay. So how to calculate burn time? Well, if we get back to one of those, you can see that the total impulse is basically thrust times burn time. So you have total impulse and divided by average thrust, you get the burn time. So in case of that motor, let's say it has total impulse of 320. If you divide by 140, it's going to give you a burn time of about 2.2 seconds, something like that. Yeah, 2.3. Yeah, if it was the higher value, it would be double than that. And when the rocket is going to reach apogee, it's basically burn time plus delay time. So it should reach the apogee in about 16 to 19 seconds. I'm just gonna draw something quickly for you to make sure that you all got it. Okay. So here's the typical flight profile. So let's say for this portion of flight, you have a burn time. Then you have, let's call it delay time. And this is the point, ideally, when you should deploy a parachute. And then the rocket slowly descends to the ground. Okay, so let's get to simulation. What's the purpose of simulation? Why we do this? The most important thing is we want to determine the optimal timing for recovery deployment. We want to know when the apogee occurred, after what time. And then there are a bunch of other things we can do. We want to choose optimal motor, choose the size of parachutes, and get to know something about mass properties, and so on. About stability, I forgot to mention something. Let's see, rocket stability. Okay. So there are two important points for the rocket. There's center of gravity and there's center of pressure. I assume everyone knows what center of gravity is. Center of pressure is pretty much equivalent, but instead of weight in center of pressure, we consider aerodynamic forces. So this is like a central point for aerodynamic forces, and it's typically close to the fins. And for rocket stability, it's very important that CG is above CP. And why is that? It's because if your rocket is tilted, if it has some angle of attack, basically the aerodynamic forces acting on fins, or let's say on CP, are going to create like a restoring moment that's going to push rocket to upright position back again. And as you probably already guessed, the longer the distance between CP and CG, the better it is, and also the higher velocity and the more stable the rocket is. So it's important, as a rule of thumb, that the distance between CP and CG is at least 1 rocket diameter or 1 caliber. So, okay, let's forget this for a moment. I'm going to show you my OpenRocket simulation. Has everyone been able to successfully download and open OpenRocket? Where's chat? Yes. Okay. Good. Okay, there we are. So let's go first through my rocket. I'm going to show you what is what. So here in this window, we've got a list of all components. Basically, all you need to have like the most basic rocket. You just need a nose cone, body tube, and fins. And all the other stuff is just to make the rocket more accurate, make the design more accurate. So as you add those components, you can alter its properties, basic dimensions like length, diameter, and so on. You can override the mass. Let's say if you've got a component, you can predict its mass, but then you put it on the weight on the scale, and it shows you that the mass is different. You can override it. So the creation of your rocket is very simple. For most of the time, you'll be using side view. You can use back view. You can rotate this. And you can see a 3D figure. This one's really nice. And you can add some appearance to your rocket. What I really like, it's just for you to play, to have fun, is the Photo Studio. You can actually make a really nice wallpaper for yourself, just as I did in here. But anyway, let's get back to OpenRocket. So when you have like a rough design of your rocket, you can go to Motors and Configuration. You click New Configuration, and then, well, you need to choose in which tube you want to mount the motor. In my case, I have two tubes. You can see there's that outer tube, and that's sort of pinky or purple is another tube. So I'm using inner tube for the rocket motor mount. Then I can choose motors, and here's the list of all commercially available rocket motors. Well, there are more of them. There's quite a lot to choose from. I recommend Aerotech motors. We're going to be using single use. Actually, that's easier. We're going to be using single use motors, not reloadable. Single use are much easier to operate. And we are looking for motors, let's say in H class. Yeah, so here's a bunch of motors to choose from. You can look at the details, and here's the thrust curve that I mentioned and a bunch of basic properties that you would like to know. So once you chose your motor, all you need to do is just go to Flight Simulation, click Run. There you have it. And what does it tell you? This is the most important thing we spoke about, optimum delay. You need to make sure that the blue thing, the delay charge, which I just erased, burns for 10 seconds. My motor says it's 14 seconds. So what I need to do is subtract 4 seconds out of it using a special delay tool. Got it somewhere in here, but I just don't want to waste time searching for it. So for my design, I picked two motors. Well, no, it was in two separate flights. This is my level 1 motor, which is quite powerful. I could go with H. It's a bit powerful. And then I went for J435 for my level 2. And this thing, it was really powerful. It was extremely powerful. My rocket is fine, but I lost it. Basically, the conclusion from this is when you do level 2, you need to have some sort of trackers. For level 1, should be okay without trackers, but with level 2, you need some trackers. So after you run simulations, what else can you do? You can plot a bunch of things. You can choose what you want these to be. You can delete them. You can plot. And there it is. So altitude. That's the altitude. The apogee would be around 1,000 meters. You can change units in the settings if you prefer some other. Yeah, and the apogee will be reached after about 13 seconds. So as you can see, optimum delay is for how long that blue thing burns, for how long the delay grain burns. And the time to apogee is optimum delay plus the burn time of the motor, which is about 2 seconds, I believe. Okay, so once again, just to show you how we designed the rocket, you can start with a nose cone, bunch of shapes to start with, use some shape parameter and see how it changes. Try to make it as accurate as you can, although you don't need to be like very specific, because the most important thing, what you need to know is the optimum delay. So all the rest doesn't matter that much for our starting point for level 1 certification. Then you do the tube, you can change the diameter, and then you do fins. You can have 4 fins. I recommend 3. There's just less chance that one of them will break. Well, and you alter all those kind of parameters. So let's say you've got your design finished. You choose the body tube to where you mount your rocket. Although I recommend the way I did this, it's way better to have 2 tubes. Let me see if I can get back to my, yeah. It's way better to have 2 tubes and have the fins going through the wall of your outer tube. If you put a lot of epoxy on it, this is going to be very solid. There's no chance that your fins are going to fly off. And for supersonic flight, as I had with my level 2, it's important to have your fins solid because they may just fly away. Okay, you choose your motor, and the motor will do, let's say, H something, maybe this one. This looks fine. It's pretty big. And you look at your stability, 0.2 caliber. That's not good enough. We need at least 1 caliber. So what you need to do, most typically you extend the length of your rocket. Well, that didn't help. That only made things worse. So what else you can do is you can add a mass component. You can add some ballast, let's say 100 grams to your nose cone. Okay, but it's not at the tip. Let's say it's somewhere in here. How's the stability looking now? 2. That's a very good stability. That's even better than you need. That's more than you wanted. So yeah, you play with all those things. You could, if you want to increase your stability, you could increase the height of your fins, but keep in mind, the bigger the fins are, the greater the chance of breaking them is. So it's better to keep your fins short, but maybe you can increase the root cord, because if you have this high, it's not a problem if you have this number high, because you're gonna have epoxy all over that length, so that's gonna keep your fins secure. You can also increase this one. Okay, so I guess I'll leave it to you guys now. Let's see. Okay, just as a practice, you can go to apogeerockets.com. Pretty good website for, come on, what's going on? It's a pretty good website to search for rockets and rocket components. You can look for some rocket kits. They have high power rockets. Okay, just to explain you, skill level is something they came up with, is how difficult it is to assemble the rocket. It doesn't have to do with certification level. It's something separate. High power rockets. Let's see. Skill level 2 or 3. Okay, let's just stick to the instructions that I have in here. Let's go to maybe skill level 3. Just find some rocket for up to $30 if you want to keep it cheap. Well, there's no. Let's pick maybe this one. Okay. And I think they have a file for the simulation that you can just open. Not entirely sure. No, this is not the file. Anyway, you should be able to find some like a technical drawing. Did I just close it? Oh no. Yeah, you can pick a rocket, try to recreate it in OpenRocket, try to create its design. That's basically what we did like in 5 minutes with Michael when he was about to launch his first rocket. And then play with various motors, see which motor you like to pick for your rocket. And most importantly, keep in mind the optimum delay, right? So pretty much, I think that's it. Let's see what else I have in here. Yeah. Okay, guys. So let me know if you have any questions. Let's see if there's a chat. No questions?
Do we know which rocket kits are we getting for our level 1 cert? Because we can try modeling that already, so we don't have to do it in the future.
Yeah, I need to double check with Andy. I'm pretty sure she's getting some Zephyr rockets. This one for sure. It's pretty expensive. I mean, for a high power rocket, it's probably not too bad. So I'm going to send you the link in the chat. Are there any specific design constraint? Well, your design constraint are your materials, and two things you need to, two requirements is at least one caliber of stability of the distance between CP and CG. And another thing, sorry, I forgot about one more thing, is thrust to weight of at least 5. What that means, let me show you on an example. You take your average thrust, which is 116 newtons. You calculate the weight of your rocket. So if I got 1,245 grams, actually, let's convert it to kilograms. What am I doing? Sorry, forgot to convert it to kilograms. Okay, that's the weight of the rocket in newtons. You need to make sure that the thrust of the motor is at least 5 times higher than this, that it's at least 60. In this case, it's 140, so we are well above it. We basically got 140 divided by 12. We've got almost 12 to 1 thrust to weight ratio. The reason why it is important is as your rocket ascends, at the beginning you have zero velocity, so aerodynamics don't work. Am I still recording? Yeah. Okay. So when you launch, you typically launch off some rail, some guide that is, let's say, 1 meter tall. And within that 1 meter, you need enough thrust that's going to get you to some significant velocity so that the aerodynamics actually start to work. So once again, 2 requirements. at least 1 caliber stability. I'm going to write it in chat. And the other requirement is at least 5:1 thrust to weight ratio. Any other questions?
One thing I'd like to add is that it's better to even have a 10-to-1 ratio. When I was at the last event, I had a ratio of 9.5-to-1, and I couldn't fly because the wind speeds were too high. So if the wind speeds exceed, I think it's somewhere in the manual, like somewhere around 10 to 15 mile per hour winds, they won't let you launch without a 10-to-1 thrust to weight ratio.
Mm-hmm. Yeah, so it's very important when you have high winds, the rockets tend to be more unstable. So the launch officer may require you to have higher thrust to weight ratio just to ensure higher stability. Okay. That's it. Thank you, guys.